Relative positioning. Relative positioning can be done in three different ways. The first one is called single difference. And in single difference, the goal is to determine the coordinates of the point B here with respect to the point A. It means that the point A is a known point and point B is unknown, and we want to determine its coordinates. So I can write a mathematical model between the satellite J and point A, the reference one, as you see here, and another one between the satellite and the unknown point B. Now I subtract these two equations. If you see here, on the left-hand side of both equations, the satellite clock is common. It means that when we subtract these two equations, the satellite clock error will be eliminated. Therefore, we have this equation without any satellite clock error, or simply I can write it like this. So in single difference, the satellite clock error is eliminated. But how can we determine the coordinates for point B? This quantity here contains both coordinates of point A and the unknown coordinates of point B. So we have three unknown coordinates here, and we have an ambiguity parameter, and also the difference between the receiver clock errors in both points or both receivers. So we can write for each satellite and each two receivers this equation. In the other case, we call it double difference. In double difference, we write the equation between two satellites and two receivers. So for example, between the first satellite, J, with two receivers, I can write a double difference equation. And with satellite K, I can write another double difference equation. And as you see here, on the right-hand side of both equations, the difference between the receiver clock errors are the same. The satellite signal frequency is always the same for all satellites. So I can conclude that if I subtract these two equations from each other, this part is to common part will be eliminated. This double difference equation is free of satellite clock error and receiver clock errors. Means that both satellite and receiver clock errors are eliminated. How can we determine the coordinate? Again, we have three unknown coordinates for the point B. We have ambiguity parameters here, and we need to write double difference between each two satellites and two receiver. Question is, we normally use more satellites than the receivers. Therefore, it is important to know which two satellites we select. Which one should be the reference for the other one, because we have to subtract the phase observations of the satellites from each other. So this is also a task that who have worked in programming for GNSS positioning, they know or they are familiar with it. And triple difference between two satellites and two receivers. And I can write one double difference for the first constellation of the satellite. And in another epoch, I can write another double difference. And as you observe, the ambiguity parameters in both equations are constant, are the same. If I subtract these two equations from each other, I get to the new equation for the triple difference. And as you observe, the ambiguity parameter is also eliminated. This means that for triple difference, the satellite, receiver clock errors, and ambiguity parameter are eliminated. But the question is this method good for positioning? Well, actually, by eliminating the ambiguity parameter, which is a physical parameter of the equations, you will reduce the sensitivity of the model to the measurements. And also, in all differencing methods that we do, by differencing equations from each other, we correlate them, we create correlations actually between the measurements and the equations. So then what this is less precise. Is ambiguity parameter is not an error to eliminate. It's part of a signal. Therefore, triple difference is a good method for determining the approximate coordinates for the points, for the unknown point, B for example, or for determining the approximate value for ambiguity parameters.